For a function y equal f of x, we know that the derivative f prime of x tells us about the rate of change of y with respect to x, which has helped us in the past and will help us in the future to locate intervals over which a function is increasing or decreasing. It turns out that locating the intervals in which the derivative of f prime increases or decreases, that can also tell us something important about the original function f. I want to emphasize here that we're talking about the rate of change of the derivative, not the rate of change of the original function, but the rate of change of the derivative of the original function, which is the second derivative of the original function f. In particular, we're going to find out that the second derivative of f tells us where the graph of f curves upward or downward. That property of curving upward or downward is called concavity. To give you a formal definition of concavity, if you have a differentiable function f on some open interval, the graph of f is concave up on the interval when the derivative is increasing on this interval, and is concave down on the interval when the derivative is decreasing on the interval. Not whether the function is increasing or decreasing, but whether the function's derivative is increasing or decreasing. The most important thing to remember here, and I'll say again, is that when we talk about concavity, we're talking about taking the derivative of the derivative, which is the second derivative of the original function. Before we delve into the details of finding intervals where functions have concavity changes, let's take a moment to focus on what concave up and concave down look like visually. For example, if I take this curve, you notice that if you start drawing tangent lines to that curve, you see that they all fall underneath the curve. So we can think about a graph of a function over an interval. The graph is concave up if it lies above its tangent lines. Or another way to say that is that the tangent lines lie below the curve. That's a region where the function is concave up. Some people say it this way, that over an interval where a function is concave up, it holds water. And you can sort of see what they're talking about there. On the other hand, if you've got a function and you're looking at it over an interval where the curve lies below its tangent lines, or again, you could say that in the reverse, that the tangent lines lie above the curve, that's an area or an interval where the function is concave down. And again, some people would describe that as saying that the function spills water. I think it's pretty obvious, holds water versus spills water. It's probably a good way to think about concavity. Now, obviously, we're going to want to find the intervals where this concavity happens. And we'll end up using the second derivative to find those intervals as follows. There's a test for concavity. If you have a function whose second derivative exists on some open interval, call it I, if the second derivative is greater than 0, that means the second derivative is positive for everything on that interval I, then the function is concave up on that interval I. On the other hand, if the second derivative is less than 0, which means it's negative for all values in that interval I, then the function is concave down on that interval. So the second derivative tells you about concavity. A positive second derivative gives you an interval of concave up behavior, and a second derivative being negative over an interval gives you an interval of concave down behavior. In practical terms, I'm going to give you some guidelines that will help you get through this in terms of just solving problems. First of all, you'll want to locate the x values in which the second derivative is either 0 or the second derivative is undefined. think back when you were doing increasing and decreasing. You were doing that with the first derivative. Now you just extend that same procedure to the second derivative, where the second derivative is 0 or the second derivative is undefined. Then you'll use those x values to determine the test intervals. Again, think back to when you did increasing and decreasing intervals. That's exactly what you did. You were doing it with the first derivative. Here we're doing it with the second derivative. And finally, test the sign of the second derivative in each interval determined by step 2, and then build a concavity chart. Thinking back to what you were doing with increasing and decreasing, you were doing this with the first derivative, what we call critical numbers, and you were building an increasing decreasing chart. Now you're doing it with the second derivative, and you're building something I will call a concavity chart. Let's look at a simple example which shows us how this test for concavity works in practice. Suppose I start off with the guidelines that we just talked about, locating the x values where the second derivative is 0 or undefined, using those x values to find our test intervals, and then testing those signs in those test intervals to build a concavity chart. Those are the things we talked about doing. Let's apply them to a really simple problem. Suppose I ask you to find the open intervals on which the graph of f of x is equal to minus x cubed plus 3x squared minus 4 is concave up or concave down. This is a simple polynomial function. As we've talked about all semester, whenever you're dealing with polynomial functions, everything works out nicely. Derivatives are easy. There aren't any values where the derivatives are undefined, so you don't have to worry about where the derivatives are 0. So a polynomial function is the perfect example to start off with as being a very basic problem to see if you understand the concept. So in any case, the first thing we do is find the first derivative, because we can't get to the second derivative without finding the first derivative. So the derivative, the first derivative of minus x cubed plus 3x squared minus 4 is minus 3x squared plus 6x. Remember, we're going for the second derivative, so now we take the second derivative. That would be minus 6x plus 6. And then we want to know where the second derivative of the function is either 0 or undefined. As I just said, for polynomial functions, there aren't any undefined values, so we're strictly looking at where the second derivative is 0. So if you set that equal to 0 and solve for x, you'll find out in this particular problem, there's only one value where the second derivative is equal to 0. What do you do with it? You take that and put it on a number line. You want to determine your test interval. So since you only have one value, that means there's going to be one interval to the left of 1 that you have to test and one interval to the right of 1 that you have to test. So what do? You take a test value to the left of 1, say maybe 0. Take a test value to the right of 1, say maybe 2. How do you test them? Remember, we're testing for concavity. That's a test involving the second derivative. So you take each of those test values and plug them into the second derivative, not the first derivative. The first derivative tells you about increasing, decreasing. Here we're thinking about concavity. So if you take the test value 0, plug it into the second derivative, you get 6. Well, 6, of course, is a positive number. Positive means that the function is concave up or holding water. So you might label it that way, concave up to the left of 1. Then you move to your test value on the right side of 1, which we chose as 2. Plug that in, do the arithmetic, and you end up with minus 12 plus 6, which is obviously negative. That's concave down. So to the right of 1, the function is concave down. Since there's only one number to test, that means you only have to test for 2 intervals. So to wrap it up, what you've shown is that the function is concave up to the left of 1, that's minus infinity to 1, and it's concave down to the right of 1, that's 1 to infinity. Keep in mind that you have to be able to do a problem like this just to make sure you understand the basics, the principles. If you can understand this problem, you're in a good position to go on to hard problems where maybe the algebra is a little more challenging or something like that. But until you feel like you can do this problem in your sleep, there's no sense in moving forward with more difficult problems where the algebra might be more challenging or there might be something else that puts a little twist in it. You have to understand this. So spend a lot of time thinking about this problem and similar problems and make sure you can handle these before you try to tackle the others. And as a matter of fact, if you look at your homework, there are quite a number of problems on your homework that you'll be able to tackle just at this level without even worrying about the difficulties. You won't get 100%, maybe you won't even get 85%, but you can do quite a bit of the work because this is the basic idea. And if you've got this, you're well on your way to doing well in this section. I do want to contrast that with an example where there might be some more difficulties. In this example, we want to determine the open intervals on which the function f of x equal minus 6 times the square root of x is concave up and down. I mentioned this problem as an illustration of something with an extra level of difficulty, and I'll show you in a minute what that is, but notice that this is a square root function. Our guidelines are the same as for the other problems. We want to find the x values in which the second derivative is 0 or undefined, use those x values to determine the test intervals, and then test the sign of the second derivative in each interval and build the concavity chart. And from that, we can read our concavity intervals. So the first thing we want to do is find the second derivative so that we can actually apply those guidelines. So we have the function. We want to rewrite that function. Instead of the square root of x, we're going to write it as x to the 1/2 power. The derivative would be 1/2 times minus 6, which is minus 3, and then subtract 1 from 1/2, and you get x to the minus 1/2. The derivative again, to get the second derivative, would be minus 1/2 times minus 3, making a positive 3/2. Subtract 1 from minus 1/2 and get minus 3/2. Now we're going to be plugging back into that value for the second derivative, so you probably want to go ahead and change your second derivative back into a radical because it's easier to plug in that way. So I would go ahead and do that. The negative 3/2 tells you it drops into the denominator, and then you have a positive 3/2, and the denominator of the fractional exponent is the index of the radical, which means it's the square root, and then you're cubing it. So you need to practice that already. If you need to go back and look at that preliminary algebra video or go practice on your own, you need to be good at this. It shouldn't take you long to do. The reason I want to do this in this problem, though, is because I'm going to be plugging numbers back into that second derivative. I didn't need to do it first derivative because I'm only going to be plugging the values back into the second derivative to determine the concavity. According to our guidelines, we look at the places where the second derivative is 0 or undefined. And this is one of the reasons I work this problem. This is not quite as simple as the other. When we're working with polynomial functions, life is always easier. Things happen nicely with polynomials. But when you have a square root, when you take the derivative, you're going to get a square root in the denominator. So you look at that second derivative as a fraction. The only way a fraction can be equal to 0 is for its numerator to be 0. Well, 3 is just 3. It's never going to be 0. So there aren't any values where the second derivative is 0, but because that square root dropped into the denominator, there is going to be a value where the second derivative is undefined, and that's at 0. If you try to plug 0 into the second derivative, you get an undefined value. But remember, step 1 says, under the guidelines, f double prime being undefined is one of the values that you need to use to determine your concavity. So I know I'm going to get a value out of the denominator being equal to 0 for the second derivative. From that, I can create the concavity chart. So 0 is the only thing going on there because there aren't any values that make the second derivative 0. There are only values that make the second derivative undefined. Another thing you've got to be careful of, and anytime you're not dealing with polynomial functions, you've got to think about the domain of the function. You've got to be really careful here because once you find the possible values you're going to use in your concavity chart, you usually test on both sides of them. But you've got to be careful here because this is a square root function. You can't plug a negative number in under the square root. So what that tells you is the domain for this function is from 0 to infinity. You can plug 0 in, any positive number, but you can't plug a negative number in, so you need to notice that. For polynomials, the domain is all real numbers, but whenever you get something that's not a polynomial, you have to look and see, is there a domain restriction? And here, there is. You cannot plug a negative number in for x to calculate the y value. So you can't even get anything over there. So the bottom line is you only test to the right of 0. There's nothing to test to the left of 0 because you can't plug a number in for x that's negative. It's not difficult, but you have to notice that. So we only have one interval to test, and a test value bigger than 0, maybe you use 1. And you're plugging 1 back into the second derivative. Remember, the concavity test has to do with the second derivative. So if you plug 1 in for the second derivative, it really doesn't matter what the answer is except that it's positive. That's all you care about. Positive second derivative means you have concave up. So the question, this problem was to find the intervals in which the function is concave up and concave down. And it turns out there's no place where it's concave down. It's strictly concave up on the interval from 0 to infinity. Please go back and look at this problem again and go through it and make sure you understand that when you're not dealing with a polynomial function, the domain issue is extremely important. You simply cannot test a value that's outside the domain of the function. With polynomials, you never have to worry about anything like that. So look at that again and go through it and make sure you understand how that all worked out. If the tangent line to a graph exists at a point at which the concavity changes, then that point is called the point of inflection, or sometimes just called the inflection point. Just to get it into your head visually, that leftmost graph is a place where the function starts off holding water and then starts spilling water. In other words, it starts out concave upward, it ends up concave downward. The point where it changes is your point of inflection. The second example does exactly the opposite. It starts out concave downward, spilling water, and then it changes to concave upward, holding water. That point of inflection is where the change happens. The third example goes from concave up to concave down. The only reason it's pointed out separately is that happens to be a place where the tangent line is actually vertical. That means the derivative would be, the first derivative, which would be the slope, would be undefined at that point. So if you want a formal definition of the point of inflection, if a continuous function has a tangent line at a point where its concavity changes, then the point is called a point of inflection. This definition should make it pretty clear that at such points as these, the sign of the second derivative changes. So if we want to locate possible inflection points, we need to find out only the values of x for which the second derivative is 0, which the second derivative is undefined. We've already practiced that. I just want to emphasize that this is what we're doing, and that it mimics what we did for finding relative extrema in critical numbers. That all deals with the first derivative, but the process is essentially mimicked again to do second derivative stuff, which determines concavity, which determines inflection points. It's a similar process dealing with the second derivative instead of the first derivative. So you think of the first derivative as being increasing, decreasing, and relative extrema. You think of the second derivative as being concavity and inflection points. But the process for doing those things is very similar. And I've said this before, but again, it's important. If the point c comma f of c is a point of inflection of some function f, then it's going to be true that either the second derivative is 0 or the second derivative is undefined. Let's do another example. It says, discuss the concavity of the graph f of x equals x to the fourth plus x cubed minus 3x squared plus 1 and find its points of inflection. You should be really happy anytime you're given a function that's a polynomial, because some of the complexity goes away. The derivatives are straightforward. There are no places where the derivative is undefined, the second derivative is undefined. It's strictly a matter of things being equal to 0. The undefined part goes away because for a polynomial function, f and all its derivatives is defined on the whole real number line. It's only where they can be equal to 0 that's going to be a thing you have to worry about. So again, we're looking for concavity and inflection points. So we go to the second derivative, but we have to get through the first derivative before we can get to the second derivative. So we start off with the original function, take the derivative, power rule, power rule, power rule all the way across. Then take the second derivative. You're going to set that second derivative equal to 0. So at some point, if this is a quadratic, you're going to end up factoring, or at least trying to factor it. Turns out here, if you factor out a 6, you get 2x squared plus x minus 1, and that factors itself into 2x minus 1 times x plus 1. If you're having algebra issues rather than calculus issues, you need to take that as a separate problem or something separately to work on, and go off and work on that, and then come back to the calculus part, because the algebra is going to be the mistake-laden area for a lot of people, and you need to work on that, because doing the calculus itself, especially with a polynomial function, is very straightforward. So in any case, I know I'm going to end up setting that equal to 0, which is the reason I went ahead and factored that. If you set the second derivative equal to 0 now, since you've already got it factored, you can see that there are only two places that you're going to get a 0. That's when the 2x minus 1 is 0, and that gives you an answer of x equal to 1/2. And then when x plus 1 equals 0, and if you set that equal to 0, you see the other one is the x equal to 1. Excuse me, x equal to minus 1. So that tells you how to create your concavity chart. You take the numbers you found, put them on the number line in the correct order, and then do test values. So you take something to the left of minus 1, something between minus 1.5, and then something bigger than 1/2. Whenever possible, choose numbers that make your calculations easier. But you're always going back to the second derivative. So don't forget, you're plugging into the second derivative. You're plugging in right here. Or you could go back and plug in here. It's just easier to plug in to the factored form. And when you do that, you're going to get, in this case, 30. You don't really care that it's 30. You just care that it's positive. A positive second derivative means you're concave up on that interval. Then you move to the second test value, which is 0. You plug 0 in, you end up with -6. Again, the main thing you're interested in is that's a negative number, which means you're concave down. And then finally, your last test value is 1. You plug that in, you end up with 12, which again is a positive number, which means it's concave up. So you have your concavity chart. The problem asks you to discuss the concavity and define the inflection point. So as you're discussing the concavity, what you're going to say is that it's concave up on the ends from -infinity to -1, and from 1/2 to infinity. And it's concave down in the middle, which is from -1 to +1/2. It also says now to find the points of inflection. Those are just x, y coordinates. You already know the x coordinates, so if you want to find those inflection points, you already know that you're going to be looking at -1 and +1/2, because those numbers came from setting the second derivative equal to 0. Because it's polynomial, there aren't any places where the second derivative is undefined. So it just comes down to finding y values. Now this is an issue that causes students trouble too. Whenever you're choosing y values, remember these are y values that you're trying to calculate here. Y values. You go back to the original function. The original function is y. F of x and y are the same thing. So you go back to the original function when you're calculating y values. Not to the first derivative, not to the second derivative. Anytime you're calculating y coordinates, you go back to the original function, which tells you what y is. Again, if you plug in -1, you end up with -2. So that's the point, -1, -2. And if you plug 1/2 in, calculate, you get 7/16. So you have 2 inflection points. If you really want to see what the graph looks like, you could see it here, and you can see the inflection points at -1 and at 1/2, and you can see the concavity matches exactly what we said it was. Practice, practice, practice. There's nothing inherently difficult about any of this, but you do need to practice, especially if you have algebra skills that need to be honed. Now, the second derivative test you think of as mimicking the first derivative test, except you're dealing with concavity. But it turns out there's a totally different use for the second derivative that I want to point out. It's actually encapsulated in something called the second derivative test. So even though we usually think of the second derivative as a tool for determining concavity and finding inflection points, it can actually be a substitute for using the first derivative test. There are cases where it fails, and I'll show you how that works. But when it works, it's actually faster most of the time than doing the first derivative test. So the second derivative test is an alternative to using the first derivative test for increasing and decreasing that fails on occasion. And I'll show you an example of that. But when it does work, it's typically a little easier, than doing the first derivative test for extrema. It works because if you think about what we know about concavity at extreme values, think about it a minute. If you've got an area of concavity downward, any relative extrema there is going to be a maximum because it's spilling water there. It's kind of like an upside down cup. It would spill water. That's a maximum. So anytime you have a relative maximum, if you check the concavity there, it should be concave down. It should be spilling water. On the other hand, if you've got an area where an interval where the function is concave up, it's going to be holding water. And that's going to be a relative minimum every time. If you check the concavity around a relative minimum, you'll get concave up. That gives you another way to determine whether a relative extreme value, in other words, whether a critical number is a max or a min. Now, I said this test can fail on occasion, and I'm going to show you that in an example. But when it does work, it gives you something that's simpler to do than the increasing decreasing chart. Just to put it in focus, let's just make it pretty clear by just listing these steps. If you start off with a function and the first derivative is 0, in other words, you're going to get your critical values, and the second derivative exists on some open interval that contains that critical value. If the second derivative at that critical value is greater than 0, meaning it's positive, a positive second derivative means you have concave up, which means you have a relative minimum. So positive second derivative tells you have a relative minimum. A negative second derivative tells you have a relative maximum, because the second derivative being negative means you're in an interval of the concavity being down, and if the concavity is down, you're at a maximum. The third step is where the test can fail. If the second derivative is exactly 0, you have to go back to the first derivative test. So you're using the second derivative test as an easier way to determine maxes and mins, but when it doesn't work, you have to go back to the old tried and true method, which is the first derivative test. Let's illustrate this with an example. And again, I want to emphasize that you never have to use the second derivative test. It's an option that might be easier in some cases than the first derivative test, but the first derivative test always works. The second derivative test sometimes is easier, but it also has a case where it fails. So it's up to you whether you want to go with the first derivative test all the time or whether you want to leave yourself open to using the second derivative test when it's actually easier. But let's look at the example. Take the second derivative test to find all relative extrema of the function f of x equals 1/3 x cubed minus 4x squared. As always, when we're finding max and mins, we have to take the first derivative to find the critical numbers. Well, the first derivative of this function is x squared minus 8x. You notice there's an x that can be factored out. So if you do that, you get f prime of x is x times the quantity x minus 8. If you set each of those equal to 0, which is what you need to do to find the critical numbers, you'll find that there's 0 and 8. Now, this is a polynomial function, so there won't be any critical numbers coming from having the derivative undefined. That's the nice thing about polynomial functions. That never happens. Now, if we're going to use the second derivative test, we have to take the second derivative, and since the first derivative is x squared minus 8x, the second derivative obviously is 2x minus 8. Now, we're going to use that second derivative to test our critical numbers if we're going to do it by the second derivative test. Remember, the second derivative is the test function to test for concavity, which tells you whether you have a max or a min. If you're concave up, that's a minimum. If you're concave down, that's a maximum. That's the first two cases of the second derivative test there. The third case is when you get exactly 0, and that's the case where the test fails. Now, if we take the first critical number, which is 0, plug it into the test function, which is the second derivative, we end up with -8. That means it's concave down. That means it's spilling water, which means you have a maximum. The second derivative test says if the second derivative is negative, then you have a relative maximum. Then we do the same thing with the second critical number, which is 8. Plug 8 into the second derivative. That tells us the concavity is positive because we come up with an 8. That's a positive number. The second derivative test says if the second derivative is positive, then you found a relative minimum. It really is just that simple as long as the test works. If it doesn't work, you have to go to the first derivative test. And you can choose to always use the first derivative test. The second derivative test is just an option. I want to end with a couple of application problems, and then it's up to you to go practice this stuff. Suppose the cost given in dollars for ordering and storing X units is given by C is equal to 6X plus 900,000 divided by X. What size order will produce a minimum cost? And we want to round the answer to the nearest whole number. First of all, when it says minimum, you know you're going to be taking the derivative. It says minimum cost, so we'll be taking the derivative of the cost function. Now the cost function has a fraction in it where the denominator is x. I would highly recommend rewriting that to make it a negative exponent. So instead of writing it and instead of leaving it and using the quotient rule, you'll end up using the power rule, which is much easier. So if you write that 900,000 divided by x as 900,000 times x to the minus 1, the derivative is fairly simple. Minus 1 times positive 900,000 is negative 900,000, and then you decrease the power by 1, which makes it minus 2. Now once you do it, you probably want to change it back because eventually we're going to have to set that equal to 0 and find the critical values. So it's probably worth changing back. Like I said, why did I find the derivative? Because I wanted to find the critical numbers, which means I've got to set the derivative equal to 0. Well, if you solve that, you can multiply through by x squared and clear all your fractions, and then add 900,000 to both sides and divide by 6, and that comes out to be x squared equals 150,000. If you take the square root of 150,000 and round it to the nearest whole number, you'll see that that's 387. Now, technically, we haven't proven that that's a minimum. That's where the second derivative test comes in. We can use the second derivative test to really confirm and verify that really is a minimum. What you have to do is you have to take the first derivative and take its derivative to get the second derivative. And notice I went back to the form of the derivative where it was written with a negative exponent because that's the easiest form of the first derivative to differentiate. So just to encapsulate what I've done, I got 387. I think that's going to be the answer, but to prove that it actually is a minimum, I have to do the second derivative test, or I have a choice of doing the second derivative test, and in order to do that, I have to take the second derivative. So if I take the second derivative of 6, I get 0, and then if I take the second derivative of the second term, I get a minus times a minus is plus, and then I take 1 away from the minus 2 and get minus 3, and then I can rewrite that with a negative 3, push it down and make it a positive x cubed in the denominator, and now I can evaluate it at 387 and see. I don't really care what it is, I just need to know that it's positive. And if it's positive, that means it's a relative minimum because the concavity is up. So now I have verified that 387 is the order size at minimized cost. So this whole second thing I just did here was the use of the second derivative test, which is why they threw this problem in when they did. But it's just to comfort me to make, I need to be 100% sure that this really is a minimum rather than a maximum or neither. And that just makes me feel better. I had a feeling that the answer was going to be 387 before I did the confirmation. The confirmation was more for my comfort level to make sure that it wasn't something hadn't tricked me, and I thought it was going to be a minimum, but it really turned out to be neither or a maximum. but I figured it would be 387 before I did the second part. With an important application in economics. It's called diminishing returns. In economics, the notion of concavity is related to that concept of diminishing returns. If we think of a function where x measures some input in dollars and y measures some output in dollars, if you draw a graph of that function, if you see this type of behavior where you have concavity upward to the left of a point and then concavity downward to the right of a point, in other words, you have an inflection point where the concavity is up on the left of it and down on the right, that's an indication of a problem that will have an answer in terms of diminishing returns. What the setup for that is, if you take, because the curve is increasing so much more rapidly before you get to that point of diminishing returns, each additional dollar of input returns more than the previous one. In other words, that's a good thing. Increasing your advertising, for instance, if you're advertising a product, might increase your sales enough to make it worthwhile. On the other hand, once you get past that point of diminishing returns, you don't get as much return for your dollar. Spending a little bit more money maybe on advertising doesn't increase the sales that much. That idea is the idea behind the point of diminishing returns. And that point, which is basically an inflection point, which is exactly an inflection point where the concavity is up on the left and down on the right, is your point of diminishing return. Typically in economics, increasing your investment beyond that point of diminishing returns, is considered a poor use of capital because you're not getting that much out of it anymore. Whereas beforehand, it seems to be a worthwhile investment. Let's illustrate that with an example. By increasing advertising cost X, measured in thousands of dollars for a product, a company can increase sales Y, also in thousands of dollars, according to the model below, and we want to find the point of diminishing returns for this product. So the equation is y is equal to negative 1/10 x cubed plus 6x squared plus 400, and that equation is valid anywhere between 0 and 40. The point of diminishing returns involves taking the second derivative. We've got to get the first derivative first, so the first derivative, just the power rule, so you're going to get minus 3/10 x squared plus 12x. The second derivative would be minus 6/10 x. I reduce 6/10 to 3/5. And then the derivative of 12x is 12. So you get the second derivative, set it equal to 0, and solve for x. So it turns out that x equal 20 is the x coordinate of the point of diminishing returns for whatever this product is. Now, if you want to actually verify that it satisfies the condition of being a point of diminishing returns, it has to be concave up on the left and down on the right. So technically, you should check this to make sure it really does have that behavior. And if you take a test value on each side, you'll find out that if you plug, say, a test value of 1 into the second derivative, you get a positive value. That means it's concave up. That's good. That's what we're looking for. If you take a test value to the right of 20, you could use 21, but why not just use 30? Seems like it'll be easier because of the 0 on the end. You'll end up with a negative number, which is concave down. That's the behavior that's indicative of a point of diminishing returns. Concave up on the left, concave down on the right. So x equal 20, and you can look at it from a graph, is the point of diminishing returns, or it's the x coordinate of the point of diminishing returns. So we still need to find the y coordinate. So you plug back into the original function. Remember, whenever you compute y values, you go back to the original function. If you plug 20 in for x and calculate, you'll get 2,000 for the answer. So the point 20, 2,000 is the point of diminishing returns. Now, be careful when a problem involves diminishing returns, because sometimes they don't actually ask for the point of diminishing returns, or maybe they don't ask for just the point of diminishing returns. For instance, even though the point 20, 2,000 is the point of diminishing returns, they might ask, either instead of or in addition to that, they might ask something like, what advertising cost is required to reach the point of diminishing returns? Remember, the advertising cost is the x coordinate, and we found out that x was equal to 20. But this is, according to the problem, x is measured in thousands of dollars. So if I'm looking for what the cost would be, it's not $20, it's $20,000. So do be careful about not only exactly what they're asking for, but make sure you've got your units right. Similarly, they might ask, what would the sales be at the point of diminishing returns? Well, remember, the sales are the y, and they're also measured in thousands. So the answer is not 2,000, it's 2,000,000, which is 2 million. In other words, add 3 more zeros. So just be careful when you're doing these problems to, first of all, know exactly what question you're answering, and also if there's a units issue, make sure you deal with that as well.